Hey, welcome. Sometimes the simplest ideas in math, the ones you think you've totally got figured out, are hiding something incredible. Today we're going to dive into a story like that. It starts with a problem you probably saw in high school, but it ends up unlocking this powerful function that's absolutely essential for modern physics, for statistics, you name it. So yeah, let's get right into it.
So let me ask you a question. What's 4 factorial? Pretty easy, right? You could probably scribble that down in a few seconds. But what if I asked you for 1/2 factorial? Like 1/2 factorial? How would you even do that? How can you multiply a half by all the whole numbers down to 1? It just doesn't make any sense, does it? Or maybe it does.
Okay, so let's just do a super quick refresh, just so we're all on the same page. You remember the factorial, right? For any positive whole number n, the factorial, or n factorial, is just that number times every whole number all the way down to 1. So 4 factorial is just 4 times 3 times 2 times 1, which is 24. Super simple, right? Clean, straightforward, no problem.
And here's the problem. This is where we hit a total wall. That definition, the one we all learned, the whole step-by-step multiplication thing, it just completely falls apart if you try to plug in anything that isn't a positive whole number. A fraction? A decimal? Nope. The whole system just breaks. The rules are way too rigid.
But back in the 18th century, one of the greatest mathematicians of all time, a guy named Leonhard Euler, he looked at this wall and basically said, yeah, we need to break that down. And the solution he came up with, oh man, it was so strange at first glance, but at the same time, just so elegant.
Okay, so this is what he came up with. Now I know, don't get scared off by all the weird calculus symbols, just hang with me. He proposed this kind of bizarre-looking integral as a completely new definition for the factorial. Think about that. Instead of simple multiplication, he was using the area under a curve. And that one shift in thinking, well, it changed everything.
See, the true genius here wasn't just finding a new way to get to 24 for 4 factorial. No, his goal was much bigger. Imagine you plotted the factorials on a graph. You'd have a dot at 1, a dot at 2, a dot at 6, a dot at 24. Euler wanted to create a single, smooth, continuous curve that would perfectly pass through every single one of those dots. He wanted to literally connect the dots.
So the big question is, how on earth can this complicated integral thing be the same as just, multiplying numbers? Well, it turns out the math behind it reveals this really beautiful hidden pattern.
Okay, so here's the key. You don't have to do the math yourself, but when you apply a standard calculus technique to Euler's integral, it's called integration by parts, something kind of magical happens. It spits out this hidden recursive pattern. What it shows is that the value of the integral for any number n is just n times the value of the integral for n minus 1. Now, does that sound familiar? It should, because that is the exact same pattern as the factorial. N factorial is just n times n minus 1 factorial. It's a perfect match.
So what does that mean? It means Euler's function wasn't just close. It was a perfect one-to-one match. You plug in the number 3, you get 6. You plug in 4, you get 24. For every single whole number you can think of, the integral gives you the exact factorial value. He did it. He successfully connected all the dots.
But remember what the real mission was. The whole point of this exercise wasn't just to connect the dots we already had. It was to find out what was lying on the line between those dots.
And this is the big breakthrough. The old definition? It was a total dead end for fractions. But Euler's integral? It doesn't care. It has absolutely no problem with them. You can plug in 2.5, you can plug in 10.1, you can even plug in our impossible 1/2. The math just works perfectly.
And that's because we're not just hopping from one whole number to the next anymore. We've got this smooth, unbroken curve. We can land anywhere we want along that curve and get a real, valid, meaningful answer. All those gaps that existed before, they're finally filled in.
Which means we can finally go back to that impossible question from the very beginning. What is 1/2 factorial? What's the exact value that lies on Euler's incredible curve right there between 0 factorial and 1 factorial?
Get ready for this. The answer is the square root of pi divided by 2. Isn't that wild? Pi, the number from circles in geometry, showing up in a problem about multiplying whole numbers. It's just one of those beautiful, stunning examples of the deep, hidden connections that run through all of mathematics.
So, as you can imagine, this discovery was way too important to just be called the extended factorial or something boring like that. No, it earned its own name, and it became one of the most powerful and fundamental tools in all of higher mathematics.
It's called the gamma function. Nowadays, you'll see it written with the Greek letter gamma. And there's just a tiny little shift in the notation to be aware of. The gamma of n plus 1 is what's equal to n factorial, but it's the same thing. It's Euler's amazing curve, all formalized and ready for modern math.
Okay, so this is a really cool story, right? A beautiful piece of math. But is that all it is? Is it just a neat little curiosity? I mean, why does having a factorial for non-whole numbers actually matter out there in the real world?
Oh, it matters. It matters a ton. The gamma function is absolutely fundamental to probability and statistics. I mean, it forms the backbone of these key formulas that model everything from, say, wait times in a queue to predicting equipment failure rates. It shows up in quantum mechanics and fluid dynamics. Engineers use it for signal processing. This incredibly abstract idea turned out to be profoundly practical.
And so the story of this impossible factorial really leaves you with a fascinating thought, doesn't it? It all started with a simple, almost naive question about something we all thought we understood, and it just blossomed into this revolutionary tool that shapes our world. It kind of makes you wonder, right? What other simple ideas, things we take for granted every day, are just sitting there, waiting for someone to ask the right question to unlock their true, hidden potential?